Welcome back to our series on electricity and magnetism. In this episode, we're going to take another look at Faraday's law, in particular, an application called Motional EMF. And we're going to look at the energy going into and out of the circuit. And then we'll follow it up with the surprising result of Faraday's law in empty space, which produces circular electric field lines. But first, Motional EMF. Motional EMF is a very common application of Faraday's law. And in this case, we're going to begin with a constant magnetic field that goes into the board away from me. And in order to generate the change in flux, we're not going to vary the field. Instead, we're going to vary the amount of this wire loop, which is actually contained within the field. Now, in this loop, I've concentrated all of its resistance into a resistor here at the end. The dimensions of this loop are going to be the width right here, that'll be W, and the length, but I'm only going to measure the length by how much of the field is actually inside of the wire loop. And so L will actually be this length right here. In order to generate the EMF, we're going to pull the loop out of the field. And in doing so, of course, we'll induce an EMF in the loop and a current flow. So I'll be pulling it out at a constant velocity V. Of course, V will be the rate of change of this length right here, so V will actually equal dL dt. And then, of course, let's look at the direction the current will flow. We know that the magnetic field goes into the board, but because we're reducing the area, we know the rate of change of flux will be positive coming into the board, back this direction. That would predict a counterclockwise current, and of course, the current is actually in the opposite direction of what's predicted. So that means the current flow will be clockwise. It will actually move this direction. And so the implications of that are pretty clear. That means the current will move upward in this loop that's actually in the field. Of course, this is now a current carrying wire in a magnetic field. There'll be a force on this wire as a result of the interaction between the current and the field. One of those forces, the one on this wire right here, will be upward. This one will be downward, and so those two will cancel. Those forces will be equal in magnitude and opposite in direction. But this one over here will be to the left. And of course, that won't cancel out because there is no such force on any piece of the wire that's actually outside of the field. It'll have no interaction with the field, and therefore no force. That means to move this at constant velocity against a resistive magnetic force, I'm going to have to put an external force to maintain this speed. If I don't, it will slow down as it exits the field because it has a retarding magnetic force on it working against the current in that back wire. Okay, so that's the whole setup of the problem. What I want to examine is the power that goes into this circuit versus the power that comes out. And here's the equations we're going to compare. The physical power of pulling on this at this velocity, again, this will feel like it has a weight to it because of the counterforce of the magnetic field. So my input force times the velocity will be the rate at which I'm putting work into it. That is, it will be the power. And of course, it's forming an electronic circuit. And we know that the energy that we input should be burned through that resistor in the form of power. And of course, power in an electric circuit, one of the methods for measuring that is I squared R. Okay, now let's use the physical parameters that we've set up here to sort of derive both sides of this equation and see if they do indeed produce a conservation of energy situation. Okay, first, the left side, the force times the velocity. Well, to do that, I'm going to have to figure out what this force is so I know how much force to apply. The magnetic force on a current carrying wire is going to look like this. It's going to be F is equal to I times the amount of wire that's in the field, and that's W, crossed with B. Of course, the current direction and the field are already perpendicular to each other, so that satisfies the cross product. This is just going to be IWB. And then, of course, to be power, we've got to multiply that by the velocity. And of course, the velocity is going to be V, whatever dL dt is. So the power for this side is going to be IWB times the velocity, V. So that takes care of the power for sort of the left side of the equation, this one right here. Now I'll do the power for the right side. For that, I'm going to have to calculate the current. And I can only calculate the current by figuring out what the EMF is. And of course, the EMF comes from Ampere's law. I'm going to drop, Faraday's law. I'm going to drop off the negative part because I've already figured out what the direction of the current is, and that's really the only role that the negative in Faraday's law does, is it calculates it as a function of the flux, but the negative just tells me which direction the current flows, and I've already identified that. So this is going to be d dt times the integral of b dot dA. And of course, I know which part of this integral the d dt refers to. It refers to the change in area as a result of L changing. The dot product is already satisfied because the area vector is perpendicular to the board in the same direction as the field. And the area is already known. That's the length times the width, L times W. So this will actually turn into d dt times b L W. And of course, we know the d dt really applies to L. So it's going to be b times W times V. So that's the EMF, and of course the EMF acts like the voltage in this loop. That voltage equals I times R, I times the current. So I is equal to the EMF divided by the resistance, and of course that's going to be equal to BWV divided by the resistance. And now in order to calculate the power from the current, I've got to square that and then divide it or multiply it by R. And of course I squared times R is going to be equal to B squared W squared V squared, all divided by a single R, because I've multiplied R times the R squared that would be there if I squared it. Well, you can see this version of it doesn't look much like this version of it, except for the fact that we haven't really substituted in the current. If the current is BWV over R, let's go ahead and do that. So if I is BWV over R times WVB, you can see what we're going to end up with here. It's B squared W squared V squared over R. And there's our proof that our input energy in the form of the force times the velocity, that produced a power input, how much energy we were putting in the circuit through mechanical energy. And of course, here's the output energy in terms of the thermal energy that's actually going to be burned in the resistor. And we see that they are identical, which shows us that Faraday's law generates a current whose energy usage is equal to the energy input mechanically. And so energy is conserved in this kind of a circuit. We'll be looking at many other motional EMF problems. Okay, our next step is to look at this circular electric field. Okay, let's take a look at this circular electric field. If we do work to move a charge, then that charge comes through the work done by applying a force on it over a distance. But suppose the force is the electrical force. Well, one way to express that is Q times the electric field that's causing the force. Well, that Q is a constant. It's just the test force that we're using to measure the size of the force. Let's divide it out so that we get the work divided by the charge. Well, one of the definitions of work over charge is the EMF. That's what EMF is. Voltage is the energy change per charge. And of course, we just looked at EMF. We looked at the way in which Faraday's law allows us to generate an EMF through the flux of a magnetic field. So let's look again at what started this out for us. It's this integral of E dot ds. Well, that looks really familiar, at least it should. The closed loop integral of E dot ds is what we just did in Ampere's law to calculate magnetic field, except now it's an electric field. Let's imagine what this would look like. If this is a closed loop that I'm going to integrate ds, that means we have an electric field that follows a path, something other than radial, because ds over a closed loop implies that we're going to loop back around onto ourselves. Well, once again, imagine the kind of situations that this change in flux involves. Let's suppose we have a region where there's a magnetic field, and this magnetic field is increasing in magnitude while it heads into the board. Well, we know what will happen. into the board, increasing in magnitude, that's going to produce a current that flows in the counterclockwise direction. But let's assume there is no wire sitting in this location. It's just empty space. I can still draw a path in that empty space. That's a fully closed loop. And what this tells me is everywhere along that path, there will be a tangential electric field, which in reality has a counterclockwise polarity. These are electric field lines, but they're behaving more like magnetic field lines. They go in a full loop and they join up onto themselves. In other words, it's an electric field that doesn't begin at a positive charge and end at a negative charge. It doesn't represent a field that gradually decreases in energy as we move from one pole to the other. Instead, it decreases in energy in a continuous loop. If I placed a charge in this field, that charge would run down the field if it was positive and up the field if it was negative. That means everywhere on this field is a different altitude, and yet it joins back up with itself at the other end. This is how electromagnetic radiation is propagated. If we have a changing magnetic field anywhere in space, it generates a magnetic field or an electric field around it, which will then subsequently generate electric field, magnetic field, electric field, magnetic field, and it will propagate. This is the core of electromagnetic radiation, and it really comes as a result of this unusual facet of Faraday's law, which is Faraday's law generates an EMF, and it generates it as a result of a magnetic flux. But in doing so, it generates circular electric field lines, and those circular electric field lines don't have to be embedded in a conductor and subsequently generate current. They're simply electric field lines that are located in space. And the implication of that is a charge in space near a flux in a magnetic field will experience an EMF which will accelerate that charge.